interval. A to B is just an interval in the domain. So let's just call it I for interval. And this is what I'm trying to do is I'm trying to make an equivalence to the region for the double integral or the solid for the triple integral. And you know how we write that is we just say the integral, instead of putting the limits a to b, I could just write your region as part of your domain as what we're integrating over. And then we have the function dx. So just to simplify the notation a little bit, we can think about the interval from a to b is just I. And let's look at I as a possible region in the one-dimensional axis of x. Just like we can look at R or D as a two-dimensional region that would have area, and then look at our E as a three-dimensional region that has volume. Okay? All right. So now let's take a look at this area and imagine taking your interval and bending it or curving it. Can you imagine that? I don't know. Anyway. All right, let's do it this way. Remember this guy? So we were introduced to this function of two variables, and then we assigned z to be the output of that function, and we decided that with the x and the y as your domain and the z as your output, your range, we have something that we can look at as a surface. And by the way, this is, what kind of a function is this? It's a what? A function of two variables. What's its output? Scalar. It's a scalar. So I wanted, the answer I was looking for was scalar function. This is a scalar function. And so has all those other functions that we put in the single, double, and triple integrals that we've been dealing with. Those are all scalar functions. So by the end of today, we're going to get our first taste of an integral where we're integrating not a scalar function anymore, but a vector field, a vector function. And we'll see that later on. But we're kind of working our way up to that. And what we have as an example, or not as an example of that, but in our steps to get there, let's imagine instead of this straight line interval and that function, let's imagine we have a curve. Let's call this curve C on the xy plane. So in this case, it's a two-dimensional curve. And then, I don't know if I should do this in red or a different color. Let's try purple. And then we know that we can project that curve up on the surface. Now, that's not really what I was looking for. What I was looking for is this area. Area that's under the surface, it's not just a curve, but I guess if you look at this as the curve, we could say it's area under that curve, but more importantly, above this curve, the two-dimensional curve, C, that's being projected up there. So when I say take this area and kind of change the bottom a little bit and make it into a curve, this is what I was trying to get at. Okay? All right, so this area is going to be given by an integral, just like we have this integral. But how are we going to describe that integral? Let's see how we could describe that integral. Well, that integral is going to, it should kind of mimic what we had before, right? So the integral should look like an integral of something. What's the base of this? It's a what? It's the xy plane, right? But the base of that looks like it's a curve. It's a curve C. So we're saying we're integrating over a curve C, and the function we're integrating is f of xy. Now that's drastically different from f of x in that, well, there's two variables now, x and y. And over here, we integrated with respect to x, and that's just the x-axis. And we had our interval I move along the x-axis, and so we knew exactly where we were going with that. But now we're integrating over a curve, which is not just a regular x or a regular y. So we need something else for the d part. But remember that the I came from the x-axis. So if we take a look at the curve, maybe we could take a look at the curve as coming from the arc length. Remember when we integrated over arc length? Now, the arc length, remember the arc length? What was the arc length like? No, you combined a bunch of things. The derivatives of what?
The partials of the
No. That would probably have something to do with x, right? What? Dx dy? Close. So the dx dy business is that if we had this curve as if we had the curve as a function y is equal to f of x. But the curves, when we take a look at curves, we take a look at curves as something else. Yeah. Dx dt, dy dt. So if we do the dx dt dy dt squared, then our differential comes out as a dt, right? And if you remember, well, back then when we first introduced the dr, we actually said the dr was actually equal to this. I don't know if you remember. Probably don't. It's all right. So that means now we're moving towards having still a single integral, but now it's going to be integrated with respect to t, which means our x and y has to be in terms of t. which, as we said, we probably want to parameterize our curve. So your f is going to be a function of x and x and y are going to be replaced with the functions with the parameters x of t and y of t. So now everything here is in terms of t, and our integral then is going to be an integral from somewhere to somewhere. From where to where? Your initial t and your ending t. So if t is equal to a starting here, and then you're going to go move along this path, and then you have t equal to b ending there, then those will be your limits of integration. The starting point and the ending point. Okay? I would like to give this a name. I would like to call this a path integral. The book does not call this a path integral. The book calls this a line integral. Now, I want to save the name for a line integral for something that's a little bit different from here, from this, but there certainly is a connection. But just for the sake of compartmentalizing our integrals, I would just prefer to call this a path integral. Okay? And we'll take a look at the difference between a path integral and the line integral. So this is the quick geometry of it, but let's do some calculations. And I thought I took the book out, but I guess I haven't. Let's take a look at the book for some examples of computing path integrals. Oh, I guess before we do that, as you can see, there's going to be a lot of importance placed on being able to parameterize things. And so we did some parameterization of things early on, and now I'm going to have to ask you to try to really remember how to parameterize. So let's take a quick detour on parameterizing important things. Parameterizing. And for now, we could just stick with 2 dimensions. But the very first important thing to parameterize is a line. More specifically, a line connecting 2 points. So this can be done either on a 2-dimensional plane or in space. And when we're dealing with path integrals, it turns out that the direction of this parameterization will not matter, but we'll see that when we move into a line integral, that there is going to be a significant difference, well, a negative sign difference between going one way versus going another way. So your direction is going to begin to matter here. Now, if you remember the parameterization for a line, I think we said we called it L of t, and then we started with a point AB, that's your starting point, plus t times a direction vector, which we have to find. And the direction vector here, if you take a look at this vector goes from AB to CD. This is supposed to be D. AB to CD. So it looks like it's going to be, the vector is going to be, what is it? C minus A, comma, and then D minus B. Wow. So the other piece of information that will be important, as you can see from our little sketch drawing over here, is not only do we need to be able to parameterize this, but we need to know where it stops, where it starts and when it stops. So the limits for these parameterizations will also be important. For this particular case, your limits are just going to go from 0 to 1. That takes you from A, B to C, D. And if you go past 1, you're going to go past C, D. And if you go negative, you're going to go before A, B. So having this parameterization is important. The only other parameterization I think that's really important is a circle, which we should all know how to parameterize, but I'll write it down anyways. Oh, by the way, this thing can get needs to get broken down to X and Y, right? So why don't we just finish that off? So X of t is equal to the first component, so this is A plus t times C minus A, and Y is equal to B plus T times D minus B. Okay. All right, now let's take a look at a circle. Let's give it a radius A. So that circle, we don't need to do much work there. You can just say X is equal to A cosine T, Y is equal to A sine T, and 0 to 2 pi. Okay? Any other business here that would need parameterization should involve some sort of other functions. What's that mean? So what I mean by that is that you can also parameterize any other function. Any other function that can be a function of one variable can also be parameterized quite easily. And what we're going to do is we're just going to keep the independent variable as your parameter t and your dependent variable as the function of that t. So if you let x is equal to t, and then your y is going to be whatever that function is as a function of t, then you would draw out the same thing, essentially be the same. And if you have x as a function of y, then you just switch the role of the t, and then you'll just be drawing it along the y-axis instead of along the x. Okay? So here are some basic parameterization. An ellipse would just be, change one of the radii for the sine or the cosine. Hyperbolas, you can probably take a look at the the eccentricity and all that stuff. Polar coordinates can be parameterized into x's and y's. So they can all be done. But here are the three basic ones that we will need to be able to do. Okay? All right, now let's take a look at some examples of these path integrals. Seem to have choices here. Number 3 and 7 are in red. I suppose that's what we want to do, right? So here we have our scalar function. Oh, they're calling it S. Can I keep calling it R? Okay. All right, so here we have our function identified. This is your function of two variables. We know we're going to integrate with respect to the arc length. And here they're telling us what C is equal to. In this case, C is the right half of the circle. So the right half of the circle, we need to be able to parameterize this right half of the circle. So let's first draw out the right half of the circle. And we said the circle was that sine and cosine combination, and 0 to 2 pi would draw out the whole circle. So we can keep that same sine and cosine combination, except we can change our t values, our t limits. Instead of going from 0 to 2 pi, maybe go from somewhere to somewhere else. So let's keep that same parameterization. X is equal to circle of radius 4, I think. Cosine t, y is equal to 4 sine t. And then as you're doing this, we should also identify the limits. So what should t go from where to where to be able to draw this right half? Negative pi over 2 to positive pi over 2. You've seen enough of that, huh? You're not going to say, like, be like a rookie and say 3 pi over 2 to pi over 2, right? That's a rookie mistake. Again, it doesn't matter for this case, but the way we parameterize it looks like we're going from here to here in this direction. So identifying the path, the direction of your parameterization will eventually be important for us. I think that's it. Well, we need to figure out what ds is equal to. So we need the derivatives of x and y. So x prime is equal to, what is it, negative 4 sine t. Y prime is equal to positive 4 cosine t. And then to get our ds or dr gets replaced with a square root of x squared, x prime squared plus y prime squared dt. So that would be square root of, this is just going to be 4 square root of 16, right? So 16 sine squared t plus 16 cosine squared t dt. And you got 16 under square root, and sine and cosine will be 1. So square root of 16 is 4. So that gets replaced with that differential. So the only thing left to do is to plug in our values for x and y. So we have our path integral is going to look like this. It'll look like x for cosine t. That's what x is equal to. Y to the 4th, that's for sine t raised to the 4th power. And then ds, which is 4 dt. And our limits, negative pi over 2 to positive pi over 2. And it's one of those integrals where we look at it and say, oh yeah, we could do this, and then we would just move on. So I think you take the constants out, those are going to be 4 to the 4th, 5th, 6th, 4 to the 6th power, and then maybe a u sub, u is equal to sine, and then that'll cancel the cosine, and then you're on your way home. Okay. All right, so that's path integral. Let's do that other one that looks kind of interesting. And you're going to get tied up with stuff like this a lot also, where your curve is not just one curve, but it's a series of curves. And so when that happens, you might have to connect them all. You have to do several integrals. So let's take a look at this one. Good to first start by sketching it out. In this case, it looks like we're going from 0, 0 to 2, 1, and then from 2, 1 to 3, 0. So we have 2 line segments to do, which means, well, unfortunately, we're going to have 2 integrals that we're going to have to do. All right, so for this, let's break this up, and let's do this carefully. We're going to break up C as C1 and C2. So C1 being this line segment from 0, 0 to 2, 1. And C2 being this line segment from 2, 1 to 3, 0. Which means now we have to parameterize each of those, and then each of those will contribute to an integral. Oh, I noticed they don't have ds either. Did you guys notice that? I didn't. I'll tell you what that turns out to be after we work this out. This isn't a path integral anymore. Well, let's use what we know and see if we can figure it out. So C1 is going to be from 0, 0 to 2, 1. So it looks like x is going to be, should we do this carefully? I was just going to do it and have you guys check my work. But all right, let's do it carefully. So from 0, 0 to 2, 1. So that means my starting point is 0, 0. Plus my ending point is 2, 1. So this just simplifies to the x component is 0 plus 2 t, and then the y is just 1 times t. Okay? So that's C1. C2 is going to go from 2, 1, and then it's going to end at 3, 0. So what's that going to look like? C2 is going to go 2, x is going to be 2 plus t times 3 minus 1, and y is going to start at 1, and the y component here is t times 0 minus 1, which is negative 1, so negative 1 times t. So we have two integrals to compute. Again, this notation is a little bit different. I didn't look at this problem carefully, but if you could try to figure out what the notation is saying, it's really just saying, well, that's dx, right? You want to replace it with something with a dt. Well, then just take the derivative of that, the first one. So let's rewrite this as C1 plus C2, and let's do them separately. So C1, I would need to take the derivative of these things. dx is equal to 2 dt. Notice the differentials, and that's exactly how we're going to replace our dx. And our dy is going to be just dt. So for our first integral, we're going to integrate this where x is equal to 2t and y is equal to t, and then the dx is equal to 2 dt. And then now back to the x squared. X squared is 2t squared, and then the dy is just dt. And then we're going to go from 0 to 1. Did you get those pieces? So this is an x plus 2y dx, right? Plus x squared dy, and that's the second part. And this shouldn't be too bad. We got 2t plus 2t is 4t, and that's 8t, and then plus 4t squared dt from 0 to 1. Can we do this? 4t squared. That's 4/3 t cubed from 0 to 1. That's just 4 plus 4/3, which is what? 16/3. So that's the first one. And then we essentially do the same thing for C2. So we need a dx and a dy again. So dx is going to be dt. dy is going to be negative dt. So we go through our integral. Our integral is asking for x, which is 2 plus t, plus 2 times y, and y is equal to 1 minus t. And a dx in this case is dt, plus the x squared, 2 plus t squared, and a dy, which is a negative dt. From 0 to 1. Okay, now I don't feel like doing this, so you just, whatever you get here, you add it to this, and then that's your total integral. Okay? Get the mechanics down for this? Yeah.
So for the negative dt, do we just distribute
Yeah, you could just take this negative sign, put it in front of this term, or if there are more terms, you put it in front of all those terms, and then just factor out a dt. Yeah. Yeah. No, not anymore. This is a little bit different. Yeah, like I said, I didn't look very carefully. I didn't really want to do this problem yet, but this is our example of what a line integral is. Integral. And I want to point out that this is slightly different from a path integral. I mean, the process, this is why it's all in the same section. That's why the book calls it line integrals. But this is a little bit different from a path integral because I want to back up and take a look at this type of integral and show you that it is, in fact, different from a path integral that we were just talking about. All right, so let's put this on pause for a minute and let's change our integral into something else, whatever that means. Okay, so what I want to do is I want to start off with a vector field first. And you remember what a vector field was? It's a field of vectors. So just randomly throwing vectors here. Some shorter than others, some longer. Okay, so I have a vector field. And what you can have here is a curve let's call that curve C. So a line integral is an integral over curve C of the vector field. But this is a vector. A vector field is a vector, right? So we need something else here. And let's develop this. I guess I'm kind of jumping the gun here. What we want to do is we want to see how the vector field reacts to this curve, or how the curve reacts to the vector field, how they react to each other. And so what we want to do is we want to take a look at at each point. Remember, a vector field is defined by a vector that's on a point. So this curve is just a bunch of points on this field, right? And so if I pick a point on this field, I will have a vector on the vector field that's associated to that. Okay? So if I pick the first point, maybe my vector field is going this way. If I pick the last point, maybe my vector field, maybe I should draw this in a different color. So I have those, if I wanted to assign every point on my curve with the appropriate vector that comes from the vector field, I would have these vectors. Okay? So what I could do is from this curve, from this starting point to the ending point, I might be interested in finding out how much work it takes to move from one point to the other along this vector field. And what I would be doing there, remember how to find work with vectors? You dot them or something, right? Force times the distance, essentially you're dotting them. So that's what we're going to do. As we're going along this curve, we're going to follow this curve via the tangent vector. And then what we're going to do is we're essentially going to be dotting at each point on this curve. We're going to dot the tangent vector with whatever vector that field is contributing. Okay? So that's how our line integral is defined, is we're taking the dot product of the vector field with the tangent vector. Yeah?
So in this specific example, the vectors in the vector field are forces when you're talking about work.
Yes. We can call it a force field. Vector field.
Does the field count in the curve?
No. The curve is independent of the field, and you just lay your curve down. The field is already existing there, and you lay your curve down, and you see how much work is it going to take to pass through that curve, given on the particular vector field. You pick up your curve and put it in another vector field, then you're going to have a different work. It does matter, but only by a negative sign, as we'll see. So I wanted to differentiate this from the first integral that we looked at, because if I kind of sum this down or pare this down into its bare bones notation, I want to kind of consider this arc length. It's not an arc length anymore. It's actually the tangent vector. So it's an actual vector. And I want to kind of consider that as dr with an arrow on top, because it's a vector. It's not the length of the vector. It's the actual vector that has, a vector has a direction and a magnitude. So if this is an integral that's being integrated over curve C, how is this different from our path integral that we saw earlier? It's what? What? It's in a vector field. So we're integrating over a vector field. So I just wanted to take a quick look at this. This is a line integral. Versus a path integral. And we see that for a path integral, we take in a scalar function over a curve C. And because it's a scalar function, we're integrating with respect to arc length, that length of the arc. So we're integrating with respect to a scalar. If we're taking a look at the line integral, we're integrating a vector field, a vector. And so we can't just have a vector there by itself. We need to actually dot it with another vector to make it into a scalar so that we can integrate it. And so that's the line integral. Okay? Does that make sense? So if we take a look at an example, wait, does this make sense, kind of? No? Okay, is there a question that you can ask? Yeah.
You just said that when we integrate this on the area?
For the path integral.
Yeah.
But for a line integral, since this is not our function anymore, this is a vector field, this is not an area integral anymore. So this actually, an example of this would be work, finding the work of something.
So want to just get this graph over here. How can you present this in the graph? What part of the graph are you talking about?
we're integrating. What we're doing is we're taking a look at dot products of the tangent vector and the vector field. Actually, I think this is r of t divided by r prime of t. Sorry. So we're taking a look at the unit tangent vector dotted with a field, and we're adding up an infinite number of them because we have to account for each point on the curve, and that's how it becomes an integral. So if we just take a look at one shot of this, just this one over here, then we have that curve, we have the tangent vector of that curve, and then we have the vector field at that point looks like this. And so we have this one thing that we're looking at, but we want that for every single point on the curve. And so Riemann sum tells us that, you know, we just do this for a handful, do this for one, do this for, you know, partition into 20, partition into 100. And so now we got 100 of these things that we're adding up, and that fits nicely into an integral. And what we're doing here is we're finding the work that it takes to move along this path with that vector field. Okay? Maybe I'm stressing this path integral a little too much, but it'll make for a nice chart at the end of the semester. Is there another question that somebody can ask? Well, if it's not quite clear, then yeah.
Can you relate this to the previous problem that you did over there?
That I did anyways?
Yeah.
Yes. So that's what we're going to do. I'm trying to remember it without looking back. All right. So say your vector field looks like this. X plus 2y, comma, x squared. Say that's your vector field. So vector field does something. And let's find a curve. Let's say a curve is going to be a line segment from 0, 0 to 2, 1. I suppose we can even try to get a graphic of this. Just to show pictures. We have our vector field, the x and dy is equal to x plus 2y and then x squared. And then we have a line segment you remember a line segment? Okay, so I think we can just say t times 2, 1. That's our line segment right here. And that's our vector field. Again, I can't adjust my vector field, but it's too small. Well, I suppose we can actually compute it. We can actually figure it out. Let's just get a picture of this. And then let's add some more vectors from the vector fields that are on the line. So if we let x and y equal to 0, 0, I think we were calling it PQ here. Then it would be 0. That's nothing. If we go all the way to 2, 1, when x is equal to 2 and y is equal to 1, what do we have? When x is equal to 2, y is equal to 1, we have 4 comma what? 4, 4. So, should be kind of. All right, let's do 1/2. So when x is equal to 1, y is equal to 1/2, we get 2 and what? 1. Oh, that just goes along the same. Okay. And then we can imagine what these other ones might be. Let's just pretend that we are computing it, and then it kind of looks like that. Oops, maybe getting less and less steep. I wonder if this is going to go negative. Anyways, the vector field applied to all those points on the curve would kind of look like those vectors. And so what I want to do is my tangent vector, since this is a line, the tangent vector is going to be the same. It's just 2, 1. So I'm just going to be dotting it with these things. And then that's going to figure out how much work I have. Okay? All right, so let's work this out as if it was set up the way I kind of introduced or reintroduced line integrals. So the line integral is going to be given by this function, or this integral of a curve over a curve, and it's dotted with r of t. I think it's just r of t. Oh, I need to look that up. Yeah, I think it's just r of t. It's not the unit vector. I'm going to have to go back and erase that. Let's finish this first. So that means I need the parameterization. So let's parameterize this line. So we already have the parameterization, right? So x is equal to 2t, y is equal to t. And then given that parameterization, your r prime vector is going to be the derivative of x and y. So it just goes there. Yes? Because I think I was mistaken. You actually don't need the unit vector. But I'm still trying to figure that out. All right, so in this f function, we want to put in your values for x and y. So that's going to give us a vector x, which is 2t plus y, or 2 times y, which is t, comma, and then we just have the x squared, which is 2t squared. So that's that vector, right? That's your f vector, your vector field. And then in that vector field, you're plugging in all the points in that line, so you're essentially plugging in the line in that vector field. And then you're going to dot it with the r prime, which in this case is just 2, 1. And then dt. And we have our limits from 0 to 1, because that's how we created our line segment. Okay? So if we multiply this out, if we take to actually compute the dot product, we're going to get 2t plus 2t times 2 plus 2t squared times 1. Oops. dt. is 2 times 1. And then integrate from 0 to 1. And I think at this point it should be clear that this looks just like the other integral that we saw. Doesn't it? Yeah.
So R of t originally was kind of like our displacement vector, right?
R of t is our parameterization for the path.
Right, which is like your distance or your displacement, right?
Uh-huh.
So why would you dot it with the derivative of your displacement, which is the velocity?
Well, another way to think about R of t are going to be, you can think of R of t as points on the curve. And we're putting those points on the curve here. And then by putting those points on the curve, we're going to get these vectors from the vector field. And then you're dotting those vectors from the vector field with the tangent vectors. And then that's how you get the work. All right, what was our answer here? 16/3. Now, the point that I want to make at this juncture is to say the 16/3 is a positive number. And it looks like the work is going to be positive when you're marching along and then the flow or the vector field or the force is going the same direction as what you're going. Okay. If we decide that we want to parameterize this the other way, what do you think is going to happen? We're going to have a negative 16/3 because we're going against the flow of the field. Okay, so when we go against the flow of the field, then we're going to get negative contributions. Because if you go negative against the flow of the field, if the field is going this way and then you're moving in this direction, what's the dot product of this? Okay, it's over, the dot product is something with a cosine, right, of the angle between them. And this angle is bigger than pi over 2. So if the angle between the two vectors is bigger than pi over 2, then the cosine of that's going to be negative. So we see that if you're going the opposite direction, then you're going to have a negative contribution. Okay? Yes. Well, you're kind of not floating; you're kind of pushing, and so I don't think that's how work works. How does work work?
It's on the surroundings. So your force is like your surroundings. So if you're going against it, then you have to do work on your surroundings. So it's negative, as opposed to if the surroundings are doing work on you and pushing you along, then it's positive.
So the work on the surroundings. What?
Yeah.
Work on the surroundings. Yeah.
External.
So let's see. So let's take a look at that line integral again, where I said the line integral looks like this. So what this means is that you can actually break up the line integral or do the components once you have the parameterization. once you have the parameterization, your working definition for this line integral is you're going to take your f, you're going to put in the parameterization into f. So putting r of t in there means you get x of t and y of t goes into x and y. And then you're going to dot it. Your dr with the arrow on it is going to be r prime of t, the derivative. And then that's going to be dt from a to b. And if you take a look at how this thing is broken up, kind of like a combination between this notation and this notation, we could take a look at capital F as a vector field with P and Q. Right? And then R prime then R prime as dx dt, dy dt. Then we can further break this notation down into just the P and Q. It's kind of understood that you're going to evaluate it at x of t and y of t, dotted with dx dt, dy dt. And then when you perform this dot product, you can imagine the dx dt times dt undoing each other, so you just have dx, and then you'll have a q, and then the dy dt dt would be just a dy. And so now you have another form of this line integral. Instead of a line integral looking like this, you have the line integral that looks like this, where each of these functions are really just pieces of a vector field, the components of a vector field. Okay? It's not okay for a lot of people. Okay. All right, well, let me just say that you can further take this to 3 dimensions, 4 and 5 if we really had to, but we need to be able to do this in 3 dimensions as well. And if you have this notation, this is kind of, general enough to say that the C doesn't just have to be in 2D, it could also be in 3D. So in 3 dimensions, you have your line integral that looks like this, but then if it's in 3 dimensions, then you know that there's going to be 3 components. Instead of P and Q, it's going to be P, Q, R. And you're dotting it with the derivatives of the 3-dimensional curve, which has an x of t, y of t, and a z of t. And then you just have another component to deal with. Okay? But the work involved in this is going to be the same. You can go with this form of the line integral where you have the dx, dy, dz, or you can do the other form where you actually think about taking the dot product. In either case, you can look at this in 2 dimensions as well as 3 dimensions. And for the 3-dimensional version, the visual with that would be the same. You have a 3-dimensional curve, like a helix maybe, and then you're seeing how much work it's going to take to go along a particular curve in your 3-dimensional field. Yeah?
When you, like in the second way that you just explained, when you write it, that way, when you like distribute your integral out, so you can take the integral of all 3 of those, the limits have to correspond to the x and y, so you just have to know that?
Yes. Yeah. So the limits have to be the same for all these. Ooh, the limits for x and y?
Yeah.
Like the t limits, right?
Oh, yeah.
T goes from A to B.
You
Or
have to
from
convert it back anyway, right?
Yeah.
T.
Yeah, so it goes, generally, this is where it boils down to.
Oh, okay.
But a lot of times it's written like this. A lot of times line integrals are written like this. I like to write my line integrals like this, but a lot of times line integrals are written like this. All right, well, try to work on the labs and see if this makes any more sense. Lab was supposed to be due at 12:45 today, but it's now due at midnight tonight.